In Chapter 2, I will briefly introduce some fundamental concepts of geospatial big data. Firstly, I will explain what is spatial data. Spatial data refers to any kind of entity or phenomenon that can be located and represented on the map. Whether it's a location of cities, the shape of a river, or changes in elevation, spatial data allows us to visualize these elements geographically. There are two fundamental types of geographic data. The first is vector data, which represents features as points, lines, and polygons. For example, a city might be represented as a point, a river as a line, and a country as a polygon. The second type is raster data, which is made up of a grid of cells. Raster data is often used for more continuous data, such as satellite images or elevation models, where each cell represents a specific value. These two types of data form the foundation of geographic analysis and mapping. This graph shows how vector data and the raster data represent the same entity. The left side is vector data. It represents an object view of the world, while the right side is raster data. It represents a field view of the world. Then what is geospatial big data? Geospatial big data is a specialized subset of big data that includes a spatial or geographic component. In other words, it's data tied to locations on the Earth's surface, such as satellite imagery, location-based services, and geographic coordinates. A significant portion of the data we generate today is geospatial in nature, and its volume is growing rapidly. This makes managing and processing geospatial data essential for informed decision-making in a wide range of fields, from urban planning and transportation to environmental monitoring. However, due to its massive size, complexity, and the potential impact, geospatial big data has become an important scientific and societal challenge. Tackling this challenge is crucial as it will unlock new insights and enable more effective decision making in both the public and the private sectors. When working with geospatial big data analytics, we face several key challenges because of the large size and the complexity of the data. These challenges fall into three main areas: data management, analysis and visualization, and the system efficiency and scalability. First, the size and speed of geospatial data are massive. It comes in real time from sources like satellites, meaning it needs to be constantly stored, transferred, and updated. Managing all this data, keeping it secure, and making it accessible across different systems can be difficult. Second, analyzing and visualizing geospatial data is complex. Advanced tools and techniques are often needed, and sometimes coding is required to handle custom tasks. Geospatial visualizations also need to be carefully customized to provide useful insights. Last, there's the challenge of scaling and efficiency. As data grows, systems must be able to handle more, which is why cloud solutions are useful. However, it's also important to optimize processes to balance time and cost. To solve the challenges of geospatial big data analytics, there are several strategies that can make our processes more efficient and scalable. First, we need to move geospatial processing from desktops to the cloud. Traditional desktop systems simply can't handle the size and speed of today's data. By using cloud platforms, we gain access to more powerful resources, allowing us to scale up easily and manage larger data sets more efficiently. Next, it's important to store data close to where it's processed. By keeping data near the tools that analyze it, we reduce delays and speed up workflows. For more demanding tasks, we can use GPU-based solutions. GPUs are great for handling complex operations like rendering large maps or running machine learning algorithms on spatial data. This speeds up tasks that would take much longer on regular CPUs. Scaling applications based on computing needs is another key approach. Cloud platforms let us automatically scale resources up or down based on workloads, which ensures that we are using just the right amount of power, optimizing both performance and costs. Finally, we should containerize applications. This allows for quick deployment, scaling, and shutting down of services, ensuring consistency across different environments and reducing compatibility issues. By moving geospatial processing to the cloud and optimizing data storage, we can significantly enhance efficiency and scalability in geospatial data analytics. A perfect example of this is our deployment of ArcGIS Enterprise on the New England Research Cloud using an educational license. This cloud-based infrastructure provides a robust platform for advanced geospatial analysis. Hosted on a Windows server with high-performance configurations, this setup allows Harvard researchers to perform complex data science tasks in a secure, scalable environment. With 16 CPU cores, 64 GB of RAM, and 350 GB of storage, researchers have the computational power they need to handle extensive geospatial data. Building on the powerful capabilities of ArcGIS Enterprise and the cloud infrastructure, we've taken these strategies even further in specific applications. One such example is OptiPath, a system developed for the Harvard Kennedy School to tackle the challenges of optimal route calculations. OptiPath stands out for its ability to provide accurate and time-efficient analysis for big data routing challenges. One of the key features of the system is its capacity to handle large datasets. It's capable for calculating optimal routes on 20 gigabytes of raster data in under 2 hours. This leverage of efficiency is crucial when dealing with complex geospatial problems, where both accuracy and speed are essential for decision making. By leveraging ArcGIS Enterprise on the cloud, OptiPath not only provides powerful geospatial processing capabilities, but also ensures scalability and flexibility. This allows it to manage the high computational demands of large-scale routing tasks, delivering optimal results in a fraction of the time compared to traditional desktop systems.